Hello, students. Today we want to talk about functions. Functions are extremely important in mathematics. I think once I read that a particular mathematician characterized the function as the most important abstraction in mathematics. And when you think about it, it is true, because as we learn the definition of the function, we learn how to describe the function and certain characteristics of the function that are useful to us, then we find that pretty much all of mathematics deals with functions. When you study trigonometric functions, clearly, when you study algebraic functions, when you study rational functions, and then, of course, as you study the calculus sequence, all of the theory is devoted to particular aspects of a function. So you really do, at this point, already understand intuitively what a function is. You've been working with them, but we haven't actually written down a standard definition. So what we want to do is think about what a function is, and then look at some notation that will help us work with functions in a way that will prepare us for pre-calculus and also prepare us for the calculus sequence. So let me share my screen. We want to start with just a basic definition. And of course, functions are things that you'll understand during the lecture, but you will continue to grow in your understanding as you take more mathematics. If you think about anything that you study or things that you have studied over many years, like languages, the more you study, the more you understand the structure. And mathematics is the same way. So let's start with a very general definition called a relation. A relation G is any set of ordered pairs. Now, we aren't specifying that the coordinates of the ordered pairs must be numbers, but in most cases, we will generally look at the coordinates as being numbers, because that will help facilitate our study of functions. But that certainly is not a requirement. We find it to be useful since we are in a mathematics class, but they could represent letters or other objects depending on what scenario you're working with. But I've defined a function here, G, and notice it has 4 elements. That is, G, the relation, is any set of ordered pairs, and we have 1, 2, 3, 4 ordered pairs. So again, a relation is any set of ordered pairs. And so now what we can think of, first coordinate, second coordinate. So first coordinate we sometimes think of as the x coordinate if we think about the Cartesian plane. And I'll abbreviate that. That's a usual terminology that we use because we think about the x and the y axis that are perpendicular, the Cartesian coordinate plane. And then the second coordinate we usually refer to as the y coordinate. Now, of course, letters don't really matter. We are accustomed to calling the horizontal axis the x-axis in the Cartesian plane, and then the perpendicular axis the y-axis. And that's what we're accustomed to. And of course, we can plot points in the plane relative to these perpendicular axes. And that was an invention of Rene Descartes, and we rely upon it. It is something that will stay with us forever. And certainly we are indebted to his genius for inventing this. Now, what we want to notice here, if we move to the definition of a function, is that we still have a relation, but there is a unifying principle that makes the relation a function. And here it is. A function f is a relation such that if we have two elements of F where the first coordinate in each element is the same number or the same element, so to speak, for instance, the same object. And in this case, I have called the first coordinate in both of these elements of F, I've called them A. So if it is indeed the case that A comma B is an element of F and the coordinate pair A comma C is an element of F, it would have to be the case that B equals C. So what that's saying is that when you associate a first coordinate with a function, then the second coordinate is unique. You don't get two coordinates. For instance, you don't get two outputs with one input. You get a single output. So what we can think of in this particular case, every first coordinate is associated with a unique second coordinate. And I don't need that hyphen there. We're assuming we would just do X and Y. So if we look at our relation G, we see 0 is associated with 2. That's good. -3 is -1 is associated with 3. That's good. -2 is associated with 3. That's good. A single input has a single output, and 5 is associated with 1/2. So what we're noticing here is we have not repeated the first coordinate of any element of G. So we see that G satisfies the definition of function. Now, often students probably don't look at ordered pairs as being something they have seen before, especially maybe in a science class or in an algebra class. Sometimes what we would do if we want to write down G, for instance, equivalently, we can say G acts upon the input 0. Put that in parentheses, and the output is 2. That is a common notation where we think of the first coordinate as being input and the second coordinate as being output. That's very important. And this notation you most likely have seen before, and it is very convenient. Let's continue. G of -1 would be 3 based upon that element of G. G of -2 would be 3. And lastly, G of 5 will be 1/2. Now, when we say G of 5, that is just a common phrase for inputting 5 into the function F. So we think of F as being maybe sorts of a machine. That is, but it has certain characteristics. That is, we make a single input and we get a single output. That is, single input, single output. Now, one thing you might notice about G, we see if we compare some of the elements, the output of -1 is 3, and the output of -2 is also 3. That's fine. It doesn't matter that the outputs for a particular input or two inputs would be the same. That is not a problem, and that in no way violates the definition of function. It does, however, bring to mind that we would say that the function is not one-to-one. That will be something we talk about later. So when we have a one-to-one function, not only do we have a function, but an instance like this would not occur. If G were one-to-one, then -1 could be mapped into 3, and then -2 would be mapped into some other number besides 3, 1/2, or 2. So if we thought of the set of inputs and the set of outputs, all the outputs would only have one person at home. It's like the input has a home, and then G maps into the output, and all of the homes have single occupancy, so to speak. That's what we're going to talk about with one-to-one function. I want you to get thinking about that right now. Later on, we'll say more about it and be much more formal in the definition. But don't have any issue with the outputs being repeated. I mean, if you think of it, let's just think of a very simple function. Now, you're thinking, when you have formulas in science classes, you usually have an uncountable number of inputs, and you normally don't think of the outputs, of course, as being a finite set because you've got an uncountable number of inputs. So what we could do is we can define functions in a more abstract way. So here's a very simple example. Let's define a function. In this case, we'll say f of x equals 2, where x is a real number. So we'll just say x is element of R. So this is probably more like what you're thinking about. And then what we want to do is think about why I've written this. Remember, I said all the set of inputs, all the set of outputs. We call that the domain for the input. So we're going to say the domain of f corresponds to the set of inputs. And the range of f corresponds to the set of outputs. And when you think about this, you should feel that you have much flexibility here and much control over the function. If you are defining the function, you can set your domain to be whatever you need for that particular problem. Or the problem may give you the domain. Or it may say, assume the domain is the largest possible set for which the function has a well-defined output. So that can mean a myriad of things. But in this particular case, what we're thinking of is that we want to input any real number, and the output will always be 2. So we can think of f this way. So f is this set of ordered pairs. It corresponds to the set of ordered pairs x, comma 2, such that x is a real number. And so we're not restricting the value of x. So any x we input, say we have f of 1/2, that would be 2. F of -5, input any real number, the output will always be 2, etc. So this is what we call a constant function. Constant function. In the sense that the output for every input is the same. And then if you think about the Cartesian coordinate system, you think, well, that graph, if we were to plot the points, that would be a very, very simple graph. Let's think about that. So again, if a function is a set of ordered pairs, and we're thinking of the coordinates as being numbers, then we should be able to plot those numbers. And then again, since the first coordinates in any two elements never repeats, then that should give us some idea as to how the graph should look. So let's go ahead and draw this graph. So we have f of x equals 2. So when we draw our Cartesian coordinate plane, do your x coordinate on the horizontal axis and do the y coordinate on the vertical axis. So constant functions are really simple. That is, you can mark off a scaling, this to represent 1 and 2. And then if we were to plot several points, they would all be along this horizontal line. So, and if this will go on indefinitely, you just extend indefinitely. So what we're noticing here, like we could just mark off a few points like a 1, a -1, a 2, a 5/2, 2.5, 3. So every input will be on this line. So I'll just notate some by coloring a little darker number, but make a disk here. It doesn't matter. All the numbers are included. So if you start by just plotting an x coordinate with a y coordinate, which is always 2, they all reside on this horizontal line. And so what we see is the graph of well, let me not let the cat out of the bag yet. The graph of a constant function is a horizontal line. Of necessity. So again, just continue indefinitely. So we think of that as being a very simple function, but maybe a useful function. We often are confronted with constant functions in our everyday life. Say if you pay an electric bill, there's a constant fee that possibly every client must pay. There may be several of them. They have a constant value. And so when your bill is tabulated, those constant pieces go into the formation of a more elaborate function. So again, when we think about a function, we think about a set of ordered pairs that has some type of definition. And so if we think again back to this definition that we have here, f of x equals 2 for all real numbers x, we see the output is always 2, and the formula is extremely simple. The output does not vary, but that makes it no less of a function. By definition, this is a function. So let's look at some more interesting examples. Now, one thing that you think about, aside from domain and range, will be some algebra functions. But before we start talking about that, let's just look at some more examples. So here's another example. And this will use some of our inequalities. So let's just say, let's use the letter G. G of x equals, let's just say the square root of 2x minus x squared. Now, when we look at this function, this is going to open the door to implicit equations and explicit equations, which is very important in mathematics, and which is what I need to talk about now. Now, when you look at this, you're thinking, well, this is more complicated than the f of x equal 2. And so now when we input a particular value of x, we have to compute 2x minus x squared, and then we have to take the square root of it. Now, this is where we need to think about sets of numbers. In this problem, I've simply given you a function defined by a formula. So you could say g corresponds to the set of ordered pairs x, comma, square root 2x minus x squared. Now, one thing that we need to specify here before we do any further work is what kinds of functions are we interested in studying at this point? We've seen quadratic equations that have imaginary zeros. For instance, when we compute the discriminant for a quadratic equation, we get a number that's less than 0, and we have to take the square root of a negative number, which we know is imaginary. The definition of the imaginary unit is set forth to deal with quadratics that have that form. We know those aren't real numbers. So what we're going to specify here, if you think about the fact that we are plotting particular graphs of functions on the Cartesian coordinate plane, at this point, we will specify that we would rather have, at this point, a real input and a real output. So what we're going to specify is this: real valued functions. So the outputs are real valued functions of a real variable. It doesn't mean that we can't have functions that have imaginary outputs. It doesn't mean that we can't have functions that have imaginary inputs. They certainly exist, and there's nothing wrong with that. But we want to start our discussion here, even though we understand what the imaginary unit is, we want to start our discussion and our knowledge of functions that have this form with real input, real output. So we say a function has real output if it is real valued. And then we say of a real variable. That means input is real, output is real. So at this point, we'll say input is real, that is real variable, input is real, and output is real. Now, of course, when you're writing a function, and this is very important, if you are the author of the function, you can specify what the domain needs to be. You can specify that. And so the domain or the set of inputs would exist by definition. Now, when you're given a function and you are told real valued function or real valued functions of a real variable, then you must do additional work. That is, you must decide which inputs will provide real outputs. And I think when you look at this particular problem here, if you were to input a 3, you would have 6 minus 9, which equals -3. Okay, well, the square root of -3 is not real. So we would not think, in this particular case, that 3 would be in the domain. because again, we are specifying real valued functions of a real variable. Again, there is no issue with considering functions that have, again, the imaginary inputs, imaginary outputs, but that's not going to be our focus, because what we are preparing for is trigonometric functions, exponential, logarithmic functions, and the calculus, where we study real valued functions of a real variable. And then, of course, when we're looking for zeros of functions, which we've already been doing with equations, we will be aware of the existence of imaginary zeros, but they will not be part of the graph of the function or our work in an important way. And so as you continue in your mathematics, you may eventually take a course in complex variables where you look at functions that are complex valued, that have imaginary outputs. So that should be a relief to you that now we just want to restrict to these types of functions. So say that to yourself many times: real valued function of a real variable. These are the objects that you study in the standard calculus sequence. And so that's what we want to prepare you to understand, so that when you take the calculus sequence, you will have sufficient background. Now, what we want to do is figure out what the domain is, and then I think it's going to be pretty simple if we do some algebra to figure out the actual range, which will be the set of outputs. So now we'll just say domain. Now, if you like, for short, you can just write DOM, D-O-M, for domain. So the domain of G would be what? All real numbers X, such that, so we're taking a square root, and so we need the 2x minus x squared to be non-negative. So this would say 2x minus x squared must be greater than or equal to 0. So again, if we take the square root of any expression and we want that output to be real, then we must again assign values to x that will what? Maintain this particular inequality. We certainly know that 3 would not be in this set. We've already seen that when we replace x with 3, the output is negative, and that will not work. So let's figure this out. Now we'll do our inequality, move away from the set theoretic notation. And so if you like, we have negative, I'll write the negative x squared term first, plus 2x is greater than or equal to 0. Now, I've already talked about boundary values, and I want to say more about it because we will be doing this throughout the course. Now, first thing you'll notice is that we don't always like the negatives on the highest power of x. So let's multiply through by -1 and reverse the inequality. So we have x squared minus 2x will be less than or equal to 0. And of course, -1 times 0 is just 0. And now, of course, this has easy factorization. So x times x minus 2 is less than or equal to 0. So now, if we think of this as zero product, when will this actually be 0? And again, what we're trying to do is figure out where the sign changes. Remember, expressions will change sign possibly at zeros and real numbers for which the actual expression is undefined. And so we want to look for those. That's what we call the BVs, or the boundary values. So again, remember, the BV stands for boundary value. So let's go ahead and plot it, our BVs. So I'll just write them here, BVs, 2, and of course 0. So we have 2 and we have 0. And of course, as I've said before, these all occur to the first power. So now we have what we call a multiplicity, of 1. And so at the 0, we would know that the sign of the function would necessarily change. That is, the graph would have to cross the x-axis. Multiplicities that are odd, 1, 3, 5, etc., provide the crossing on the x-axis. The even multiplicities, 2, 4, 6, etc., just do a touch. That is, the function will become 0, but it will not cross. It will maintain sign. Okay, so even an odd multiplicity can be very, very useful when we're talking about solving inequalities. They make our work much quicker. So now, of course, if we were to replace x with a really, really large number like 100, this product would clearly be positive. So we can say plus, so we cross, we're negative, and then we cross again. So we have plus, minus, plus. Now, when we look at this, we need less than or equal to 0. So what's nice about this little diagram here is that we see that the sign is negative, and we say below the x-axis, just to kind of give us a visual with the number line, we have the sign is what? Less than 0 when x is between 0 and 2, and equal to 0 when x equals 0 and x equals 2. So that gives us the values for which this particular expression is less than or equal to 0. So this would imply, well, for instance, we start out with greater than or equal to 0, and then we flip it around because it makes it easier to solve. So this will say x must live between 0 and 2, but we include the endpoints. So this gives us the domain of G. So again, many times when you have to compute the domain of a function that has radicals, you will do this kind of algebra. That is, you want to find values of the variable for which the expression is non-negative. And that may mean by the time you're done that you flip the inequality because you multiplied or divided by a negative value, which is fine, no problem. This inequality is equivalent to that one. So that's why we can do that. That's what's so nice about real numbers. They have really, really nice algebraic properties. So now when we look at this, we have the domain. We have all values of x that can be input that will guarantee an output that is real, okay? So now you think about that, okay? And we'll talk about when we divide by variables, how we can also compute a domain. But this is one of the most important algebraic strategies that you will use. You will always be confronted with square roots, even cube roots, even nth roots. Even nth roots are always going to be more difficult. The odd nth roots have no issue with negative numbers, okay? You don't have to worry about excluding things. When you take the cube root of a negative number, it's real. The square root of a negative number isn't. The fourth root of a negative number isn't. It's just the even nth roots that require more work. Now, let's go back to what we were working on and think about what the range would be. So we have f of x equals the square root of what? 2x minus x squared. Now we're going to use our y variable. Now what's interesting is there's no reason why we have to always say f of x equals the expression in terms of the independent variable. We can just call this y. So often we'll just say y, and we'll use the notation y equals f of x, because the second coordinate is determined by the function equation, so to speak. So we can say f of x equals the square root of 2x minus y squared, or we can just say y equals the same square root, because the value that we put into the second coordinate is just the value of the function. Okay, so when we think of an ordered pair, we think of x, comma, f of x. Or if we're just thinking of this association, we're just saying X comma Y, where Y is governed by the formula f of X. So that is a common notation. And we do that because, again, we think of the input axis as being the x-axis and the output axis, which is vertical, as being the y-axis. And one more set of terms that you may find to be useful. The input variable, whatever it may be, you may be in a physics class and the input variable is t for time, okay? So the input variable is called independent. That is, the input variable is something from the domain. You put it into the function machine, and then out comes the y coordinate or the output. The output depends on the input. So we say the output variable, which in this case is the y, is called dependent. Dependent. That is, the f of X depends on the X, the Y depends on the X. The X does not depend on the Y unless we just reverse the roles, okay? So there is nothing sacred about how we decide to choose letters, okay? We are accustomed to the independent variable being X and the dependent variable or the output variable being Y, but we could certainly interchange those. We could use other letters altogether. So do not place any information on a function when you think, oh, it should be this way. No, whatever letters, whatever notation is presented to you, that defines the independent variable. And then whatever you get by evaluating the function gives you the output or the dependence, the dependent variable, okay? So if we put in a specific value for X, we get a specific value output. So the output depends on the input. So again, when we're thinking with this notation here, we have this set up between the independent variable, which we're now calling X, and the dependent variable, which we're calling Y. But remember, as a STEM student and future STEM professional, you can choose any letters you want, and you can establish independent and dependent variables as you need to solve your particular problem. Now, let's go ahead and square. Remember when we were solving the radical equations? If we wanted to get rid of a radical, we would square. Let's see how this equation looks implicitly. So let's square. And we're going to get an equation that you've seen before. So we have y squared equals negative x squared plus 2x. Again, when we square the radical, we're relieved of it, and we just have the negative x squared plus 2x. Now what we can do is complete the square in x, and then you can see that we're going to have the equation of a circle. So now take everything over, x squared minus 2x, and we want to leave some space, plus y squared equals 0. So now what we can see is we can complete the square. Again, we take half of -2, which is -1, and square it. That gives us a 1. And then, of course, we add and subtract that. But now this gives us the perfect square. So we have x minus 1, quantity squared, minus 1 plus y squared equals 0. And now just transpose the 1. So we have x minus 1, quantity squared, plus y squared equals 1. Now, this is an equation of a circle, which you know from your geometry class and also your algebra 2 class. So when you look at this, you're thinking, oh, when we think of the graph of our function, it's just going to be one of the arcs of the circle. It could not be the entire circle, because if it were, then we would see that, for instance, if you think about our domain here, let's go back to our domain. We have 0 to 1. So you're seeing here that the center is just 1, 0. We have a center of 1, 0. And so if we drew the entire circle, we would have the input 1 having 2 outputs. And of course, that wouldn't work. And what we notice here is that the positive arc, or the principal square root, gives us the non-negative values, and the negative of this gives us the what? The negative values of the function. So we can easily draw this. Circles are easy to draw. These are the simplest conic sections. And of course, the radius is just 1. Remember, that's r squared. The radius is 1. The center is 1, 0. We'll spread it out a little bit. 1. And then we'll put our 2 here. So we have our domain 0 to 2. And then, of course, we have the radius. We can just do 4 points, and then we can sketch our circle. So when we look at this part, this gives us the function. This gives us f of x equals the square root of 2x minus x squared. Because we can note f of 0 is clearly 0. We know this. And then f of 2, well, let's just substitute. We have 2 times 2, which is 4. And of course, 2 squared is 4. Square root of 0 is just 0. And then, of course, the center of the circle, f of 1, will be the square root of 2 times 1, which is 2, minus 1, which is the square root of 1, which is 1. So we've got some simple points here. 1, 1, 2, 0, and 0, 0. So we know we have a circle, and so we just have the upper arc. And then, of course, in red, I'm just going to draw in the lower arc. This is the so-called lower arc. And this would be, we could call it another function, call this h of x, will just be the negative of the square root of 2x minus x squared. So lots of times you'll see in homework exercises where they say, if you look at the graph of a circle, you would say, would that define a function as we understand it? And of course, you would say no, because now you see that if you had a function here, you'd see that 1 would have an output of 1 and also an output of -1. And that wouldn't make sense. A function does not provide 2 outputs for a single input. We know that's one of the defining characteristics of the relation for it to be a function. So if we are to restrict to either the blue arc, the positive square root, or the red arc, the negative square root, then we have a function. So just remember, as you think about the particular formula that you have for the function, you can apply any algebra. And notice at this point, this is what we call an implicit equation. Implicit in this particular equation is how we find the other functions. That is, we say this function implicitly defines f of x, and it implicitly defines h of x. Because if we work this backwards, throw everything on one side and apply the square root principle, y is plus or minus a square root, which gives us these two functions. So to work this backwards will give us this function and also this function. But by squaring, we simply are able to recognize the existence of a conic section, a circle formula, which are easy to recognize. And then we can say, okay, now not only do we know what's going on with the domain, this also will imply that the range, in this case of f, is easy to determine. It'll just be all the possible y values, which will go from 0 to 1. So we'll say 0 to 1 inclusive of the endpoints. So what's interesting about most functions is that there will usually be an algebraic mechanism to find the domain. That is, we simply look to solve equations. That is, we solve equations if we're trying to do inequalities, finding the BVs and then doing a sign test, or we want to avoid division by zero. Division by zero would not give us a real number. It's undefined. And also, like I said before, utilize any technique you have if it will reveal a pattern that you already have an understanding of. The patterns are how we do the mathematics. Now, what we're going to find is that in some cases, it will be very difficult to figure out a range. Ranges can be complicated as the functions become more complicated. So what we will rely upon is the calculus. So when we know calculus, we will have a better understanding of limits and optimal values. So don't let that discourage you. We still will be able to do plenty of work with our algebraic techniques. It's just that we will need the derivative to be able to isolate particular optimal values, that is maxima and minima, which will give us a better indication of the range of a function. Now, the limiting processes as x would get large, or is that we would, for instance, define a vertical asymptote, which will be coming up in the later lectures, that will also give us plenty of information. So we're going to add to what we can do in college algebra and eventually pre-cal, and take all of that information with us to calculus to be better equipped to do the calculus. Now, one thing that we want to notice here is that there are a couple of things that we do working with functions that seem to be very straightforward, but we need to give them some names. For instance, the first is called the x-intercept. The x-intercept is important. We'll say x-intercept of the function f. This corresponds to x in the domain of f such that, and we've already done this, such that f of x equals 0. We already see that we have two x-intercepts of 0 and 2. We did those when we found the boundary values, because f of 0 is 0 and f of 2 is also 0. And so an x-intercept would be basically where the graph intercepts the x-axis. But we don't even have to think of intercepting the x-axis. We may just want to know zeros of a function if we're trying to solve an inequality, and maybe we're not completely interested in sketching a graph like we did here. Now, the y-intercept is even simpler. So the x-intercept is basically solving equations that we've been doing in our previous work. The y-intercept of f is basically f of 0, given 0 is in the domain of f. It's important. For instance, the y-intercept is just the value f of 0. Well, if you input 0 for the value of x, that puts you on the vertical axis. And so now you see that the y-intercept here corresponds to one of the x-intercepts. So when we look at the fact that we just simply substitute the value of 0 in for x, we do get 0. So we see that the y-intercept corresponds to one of the x-intercepts. So again, this doesn't require solving an equation. We just have to know that f of 0 makes sense. And if it does, well, it will make sense if 0 is in the domain of f. If it's not, then there is no y-intercept. And then, of course, we don't have to have x-intercepts, right? X-intercepts are simply zeros of f. Sometimes students think those are different. The x-intercepts are just also called the zeros of f. So you can write it that way, the zeros of f of x, the zeros. So there's nothing new between the x-intercepts and the zeros of the function. They are describing the same thing. And so don't look for any additional strategies that you will need there. It's the same problem to solve. Just note that we often find it convenient if we're trying to sketch a graph, just like we had here, if we know the x-intercepts. And then plus, note, because we were able to figure out the implicit form, and that's what I should write here. This is an implicit equation. So students might think, well, does this equation define y as a function of x? Well, not in the specific sense, because you have to apply the square root principle to find particular functions. So we see that it actually defines two functions, not a single function. So implicit equations can be very useful to us, but again, we know that if we do have an equation and the y variable is squared, then that implicit nature does not provide for the single function definition. And so we would say no. But again, what's important here is that by squaring, we see a form that we understand. We see the form of a circle, and that helps us with the actual graph. So when it comes to figuring out functions, we want to think of some of the most useful ways to write a function. We like the function notation. We like replacing f of x with y because we think of f of x as the y coordinate. And then we apply our understanding of range and domain, domain being the possible set of real inputs, the range being the set of outputs. So again, remember, with the domain, you have flexibility. But if the domain is not prescribed, then the tacit assumption is that we're looking for the largest set of real numbers for which the output is real. So again, remember, real input, real output. And what we have found here with the previous example here, and I keep going back to it, is that the largest set here for the domain is exactly that, the interval from 0 to 2, including 0 and 2. So function analysis is really dependent upon the particular example that we're given. So we can't say that domains are going to be a certain form. We can't say that ranges are going to be a certain form. We have to figure that out. Now, one thing that's actually kind of useful, and I want to show you, is the difference quotient. When you take the calculus, you'll do two forms of the difference quotient. So we'll look at a fairly straightforward example. I'll have this function. We have f of x equals 2x plus 3. So this will give us some work with some fractions. 2x plus 3, x minus 1. So I want to just look at this as a difference quotient, and then we can also look at range and domain and talk some about that. But notice when we look at this particular function, it has values or variables in the numerator and also variables in the denominator. So before we actually start looking at the difference quotient, let's go ahead and think about the domain. Remember, in this case, we don't have any square roots. And again, we are considering real valued functions of a real variable. The x's are real, the outputs f of x are real. And so now we have a much easier time of this. We just need to make sure that we don't divide by 0. So we see the domain of f will be all real numbers x such that x minus 1 does not equal 0. Well, that's really simple. We just kick out 1. So just solve for x, and we have x is not equal to 1. So we'll say this just equals the following set in interval notation: negative infinity to 1, union 1 to infinity. So basically what we've done is we've excluded 1. So we just say exclude 1. So again, if x minus 1 is not 0, x cannot be equal to 1. So we just say corresponding to x not equal to 1. And then if we write the interval notation, we simply use the parentheses to exclude the 1. So that's really not leaving out much, is it? One real number out of the entire real line, it has no impact really. The real number line is uncountably infinite. So if you pull out a point, it's not going to make any difference really. But it is important relative to the function, because what we're going to see later on is that this particular 0 in the denominator defines a vertical asymptote. And as x approaches 1 from either side, from the positive and negative values, the function will become unbounded. And that's something we're going to talk about in this class. And then you're going to look into in more detail when you talk about infinite limits in calculus. So we're trying to pave the way for that. So another thing that you might notice, because of what I just said, is that we have this neat little ratio here, 2x to x, because these are what we call the dominant terms. The degree of the numerator is 1. The degree of the denominator as polynomials is also 1. So the dominant terms are 2x and x, and that ratio is actually 2. So what we're seeing is that it will be very possible for the function value to get very close to 2 as x becomes positively and negatively infinite, but it can never equal 2. So in this particular case, this implies that the range of f will include all real numbers except 2. That is, f is approximately 2x over x for x approaching infinity and x approaching negative infinity. And then, of course, the x's absorb, and that gives you 2. So we think of the 2 as what we call a horizontal asymptote. So we're developing a vertical asymptote, x equal 1, and a horizontal asymptote, y equal 2. And we'll say much more about that. But I want to already start thinking about this before we actually get to it. So we could say x equal 1. We're going to say VA for vertical asymptote. And we're going to have y equal 2 for horizontal asymptote. And that'll be notation that we'll use later on. I want to go ahead and just make you aware of it, because I think what you're going to find is that the more we talk about this stuff, the more we set the road for it or set the information for it, it makes the transition much easier when we actually have to define them formally. So now we're looking at a very interesting function, maybe not as complicated as the square root. I mean, we didn't have to solve a complicated inequality. And so now let's look at what we call a difference quotient. What we can do is write the following. That is, this is called the difference quotient, which is really the slope of the secant line. Difference quotient. And so in this particular case, we're just going to say h does not equal 0. So we're going to have f of x plus h minus f of x divided by h. Now, the reason this is called the slope of the secant line is that we can think of the actual functions as being the y-coordinates. So you have 2 points for every x. That is, we have x, f of x, and then we have x plus h, comma, f of x plus h. So h is not equal to 0, so these are 2 points on the graph, and we can join them, the 2 points, to form the secant line. Just like a tangent line later on in calculus, the secant line joins 2 points on the curve of a function or on the graph of a function, as we've drawn before with the circular arcs. And so when we think of the difference in the y-coordinates, we simply get the numerator, and the difference in the x-coordinates, the x is absorbed, and we're just left with h. So we can think of this as a change in the y-coordinate over a change in the x-coordinate. That's what we call the difference quotient. And the terminology is actually quite good. It's exactly what we're doing. And so now what we want to do, it's very simple. Using the function notation, we simply replace x with x plus h for this piece. We simply write f of x and we divide everything by h. This is one form of the difference quotient. There'll be another form that you'll use in calculus, which will be much more convenient, but we need to start somewhere, and this is a good place to start. And I'll say something about the other form as we continue with our work. So let's do this. Let's go ahead and write the 1 over h out to the side just to get it out of the way. And now we'll replace x with x plus h. So we have 2 times x plus h plus 3 divided by x plus h minus 1. So replace all the x's with x plus h. And now we just write the function. We're like court reporters, okay? Now, when you look at this, you look at this as being kind of like an indeterminate form, because if you replaced h with 0 or allowed h to get really close to 0, this would just be what we call 0 divided by 0, which of course makes no sense. That's why we call it indeterminate. So what we want to do is figure out if there's some hidden property that we can't see as it's written in this form. And we can do that by doing some very simple algebra. Notice we have an x plus h minus 1 factor, and we have an x minus 1 factor, which will be our common denominator. So let's go ahead and do that. Just leave the 1 over h to the left, get it out of the way. It would just be in the way otherwise and just cause us a lot of grief. So now, if you will, you can look at this and keep it just like it is when you multiply. So you have 2 times x plus h plus 3 times x minus 1 minus 2x plus 3 times x plus h minus 1. So we're getting a common denominator. And then divided by x plus h minus 1 times x minus 1. So again, just like doing the least common denominator in our equations, when we clear the denominators, the common denominator is x plus h minus 1 times x minus 1. And that, again, we must, again, multiply this numerator by this denominator since it's not here. And we must multiply this numerator, retaining the minus sign, by this denominator. Now, if you like to keep things simpler, you can just go ahead and think of this as one piece and that as one piece. And if you want to go over here, think of the x plus h as one piece and the minus 1 as another. So you can just put some, simple parentheses right here to make that as one piece and then do additional algebra later. So this gives us 1 over h. And so now we're going to multiply in this particular case by x. So we get x times, and go ahead and multiply this out, 2x plus 2h plus 3. And then we hit everything with a minus 1. So we have a minus 2x plus 2h plus 3. So we multiply the 2 times the x plus h plus 3 times x, and also multiply it by -1, and that makes that simple, which is an improvement. And now we're going to say we've got minus 2x plus 3 times x plus h, and then we have minus minus, so we have plus 2x plus 3 times a 1. We like multiplying by 1. That's really easy. So again, we have the minus minus, so those absorb, as they say, and we just have multiplication by 1. Now, sorry about the long division lines. They're just kind of come along with the territory. Now, of course, if you like, we could just move that out to the side, and we may do that with the next computation, just move this out here and then try to absorb later to not have to write that long line every time. So now let's keep moving with the calculation. Let me move this sheet up. So now, if you will, we can go ahead and move everything to the exterior here. Let's see, we have the 1. Just going to ahead and move this out. We have the h. We have x plus h minus 1 times x minus 1. We'll just move that right there. That way we don't have to keep writing a long fraction bar, which is really kind of wasteful. So now let's see what we have here. We've got x times all of these. So we have 2x squared plus 2xh plus 3x. And then, of course, now we have a minus sign with all of these. So we have a minus 2x minus 2h minus 3. And now we can just do distributive law here. So we have a negative 2x squared. And then we have a negative, then we have a negative 2xh. So multiply the 2x times the x and the h with the negative sign, and then now multiply the 3 times the x and the h. So we have minus 3x minus 3h. And then, of course, we just got the 1 there. So plus 2x plus 3. So we don't need another division line. So again, let me just reiterate what we've done here. We do, using the distributive law, x times 2x is a 2x squared with a minus sign, x times 3, or excuse me, h times 2x, 2xh with a minus sign right there. And now we multiply the 3 by the x and the h. And you can do this in either order. So we have the 3x with the minus sign, and we have the 3h with the minus sign. And of course, this is just 2x plus 3 times 1. So notice here, if we write our arithmetic this way and not try to do all the multiplication in one line, it's a lot easier to check the work. And then, of course, over here, as we multiplied, these were simple. This was a little more complicated because we had 2 binomials. Now notice we can absorb. So the 2x squareds, they go away, so gone. Again, just use the boxes. That's the easiest way to do it. The 2xh's absorb. So this is the fun part. This is where all the algebra pays off. The 3x's absorb. And now we've got the 2x's. And then the 3's. Right there. Now what survives? We have a minus 2h and a minus 3h. So I'll put just like kind of red under those that they survive. So we'll just say survives. I always like to do this, especially when I do telescoping sums in calculus 2. We always want to know what term survives so you can check your work. So now notice everything goes away except the important stuff. So that's a negative 5h. And so we have the h, x plus h minus 1, x minus 1. So the h's absorb right there. And this gives us a negative 5. And we have x plus h minus 1 times x minus 1. Okay? Now notice, this is what's interesting about these calculations. When you do the difference quotient, I'll move this back down, the key is to absorb the h, because in the calculus, the definition of derivative is indeterminate. So what we teach you in college algebra and pre-cal is to work with the difference quotient, the slope of the secant line, so we can discuss the tangent line. So we do the algebra using the function notation, which is very straightforward. Replace x with x plus h. And notice when we do the common denominator, basically all the terms absorb except the term that contains the h, which absorbs the h here. So now this makes sense. For instance, as we take the limit as h approaches 0, this quantity actually will make sense. And this is what's important to learn about the difference quotient. So now what you can do is just make the following observation. And I'll do this in blue. Observe. That is, replace, and this is easy to do, replace h with 0. That is what we're allowing to do. We're saying h is approaching 0, getting as close as you like. That's what we're going to do. And you can see with this particular form, so this will give us, again, the h approaching 0, let it replace it with 0. So we get negative 5, and we get h is 0, x minus 1 times x minus 1. And that gives us a negative 5 divided by x minus 1 quantity squared. And that, ladies and gentlemen, is actually a formula for the derivative where it exists, even without thinking about the calculus. So what we're seeing here is that when we computed the domain, we had to kick out 1, and clearly in the formula for this, which we're now calling a new function, it doesn't make sense at 1 either. And that's not a surprise. When you think about this, when you try to construct secant lines, you have to take points that are on the graph. If you're constructing, if you think back to high school geometry, and you drew tangent lines, which only intersect a curve at 1 point, you certainly couldn't do it at 1, x equal 1, because that's not even a point on the graph, because it doesn't make sense. So what we're finding with this calculation is that with this work of doing the difference quotient, as we have here, we end up with an expression that actually makes sense when h approaches 0. And that's the whole reason we start doing this in college algebra, to get you ready for that kind of calculation. And what you're finding is that the algebra is fairly simple. And like I say, you get the fun part of seeing that most of the terms just absorb, and then you can retire the h, which is the complete issue from the very beginning. Now, I'll write a notation here. If we think about the original function that I'll move over here, this actually is what we've done. We've done 2x plus 3 divided by x minus 1. And this is a prime notation for the derivative. This actually equals minus 5 x minus 1 quantity squared. And now, when you take the calculus, there'll be a very simple way to compute the derivative of this. And let me just show you some algebra. I'm not going to tell you what I'm going to do. I'm just going to show you some algebra. So here, this is going to tell me to do this. I'm going to write some algebra down. I'm going to have a 2 times an x minus 1. And then I'm going to have a minus 2x plus 3 times a 1. And then downstairs, I'm just going to square the denominator. Okay, you're thinking, boy, this is easier than the difference quotient. Now notice we get some terms that absorb. We get 2x minus 2, and then we get a minus 2x minus a 3. And then we have x minus 1 quantity squared. And notice the 2x terms absorb. And we're left with what? Negative 5 over x minus 1 quantity squared. And you're thinking, look how quickly I got to that, and look how much work that took. We started with the difference quotient, we did the functional algebra, we absorbed all the terms, we let h pass to 0, and we got this. But then this calculation took just a couple of steps, and we have the same response. So this is what I want to basically emphasize. When you think about calculus and you think about the STEM preparation for that, we work with functions. We work with functions over and over. And so we have to get very comfortable with this kind of notation. We have to get comfortable with replacing x with, say, an x plus h, and then doing the requisite algebra with the common denominators. So what you're seeing here is that we will teach you ways to work with difference quotients by definition, and then we're going to teach you ways that the difference quotient actually provides theoretically as a route to the same response with much less work. And what we're going to find is that the level of abstraction that we introduce in college algebra and pre-cal, that prepares us for the abstraction that we'll have to use in the calculus. So there's a very definite reason why we want to work with these types of functions and do this kind of work, because it will prepare you for the solid background that you need to study the calculus sequence. Now, we have one more example that we want to talk about. Again, graphs of functions are fine, but we have to get the graph by understanding the actual function, okay? So it's fine if you want to look at a picture of a graph and make some observations about the domain and range, which we talked about with the circular arc. That's fine. But remember, the main focus is starting with the functional equation and then deciding what the graph is, because we have to come up with that because we understand the function. So I don't want you to think that graphs of functions just magically appear and, oh, there's what I need. No, that's the reverse of what happens in mathematics. We get the function equation, and then we understand what the graph will look like based upon analyzing it, looking at intercepts, looking at zeros, like I say, the x-intercepts, the zeros, the y-intercepts, looking at algebraic qualities, range and domain, things like that, comparing it to functions we already understand, like circles, quadratic functions, things that give us some idea as to what the graph should look like, and just using a lot of intuition. So just remember, you have to come up with a picture. And so as you continue in the STEM preparation for calculus, we will find techniques in calculus that will allow us to draw a graph with complete detail, which won't be available to us until we understand the derivative and its theoretical consequences. But we have to build up to that, right? So be patient. Just remember, it will all get there. Now, there's one other example that we've just been working on. I just want to go ahead and say a little bit more about this and answer a few more questions. I've got some things that I want to say here. Yeah. It's a similar function to the one we just did. Let's see what I did with that. Oh yeah, here we go. So I did that difference quotient so we could actually look at this example. Now this will seem really simple after what we've been doing. Notice this function is just like the last one in the sense that we have a variable numerator and a variable denominator. Now, what do we do with this? Well, what you're going to find as you work through homework is that you will be asked a series of questions. We've already talked about intercepts and zeros. That's easy. We'll work through that pretty quickly. We've got a domain, which we've already know how to compute. And then we're asked to work a problem backwards. What is it? For instance, if we input a value of x, that is, if we take the independent variable and assign a particular value, then we can compute the value of f at that particular value by using the functional equation. That's fairly straightforward. Now, of course, what we might be given is an element in the domain, in the range of f, and then we have to take it backwards. That is, if we start in the domain, we can easily go to the range. But what if we start in the range and then we're asked to go backwards, okay, backwards into the domain? You're thinking, well, that's what you were saying, Professor Ollis, about range and domain and one-to-one, because think about it. If we're in the range and the problem is saying, what's the value of x that maps into that value in the range, we would be thinking that there would really only be one if the reverse path were to make any sense. And then, of course, if we were dealing with a constant function, we'd know there'd be only one house in the range and everything maps into it. So there really is no reverse path. I mean, they're infinitely many. So oftentimes what will be the case, and I don't want you to think it's going to be a one-to-one function, but the equation will be solvable, and you may determine that there is actually one element in the domain that maps into it, or you might find two or three if you're thinking about a zero. It just depends on the nature of the function. And again, this is all highlighting the fact that if we were always going to be able to return in a very logical way back to the domain, that would require a very special function, like I mentioned before. That's called the one-to-one function. That is, if we move into the range, there is one path that takes us from that domain element to the range, and there's exactly one path that takes us back. That is, all the residents in the range have one occupant, okay? And so the path in reverse is set for us. So you're thinking a one-to-one function actually defines a reverse path. And so do we need to actually change what we talk about with the reverse path? Well, in some cases, yes. And I'll talk about how we do that. It's just important to realize, however, that when functions can be so-called inverted, that's only because the functions start out as one-to-one. And that'll be something that we'll talk about more as we gain more experience. So I just want you to be aware of that, because when you look at some of these questions here, you might be thinking, why am I being asked to go backwards? What's going on here? Okay, so just keep thinking about that. Again, I don't want things to be a surprise. I want to set you up for the understanding and give you something to think about, so that when we get to that point, you'll be like, oh, we've already been talking about this. And that's really my goal throughout the class. Now, notice for A, we've got this function right here, f of x equal 2x divided by x minus 2. So for A, we just want to check to see, is this an element of the function? That is, let's check out what f of 3 is. Very basic. So we'll just replace x with 3. So we have 2 times 3 divided by 3 minus 2. Of course, that's 6 over 1, which is 6. So yes, we'll say 3 comma 6 is an element of f. Again, we say f of 3 equals 6. Therefore, the ordered pair 3 comma 6 is an element of f. Now, again, when we think about ordered pairs, we're always thinking about what the graph would look like. So when we would plot the graph, or when maybe we'd sketch the graph, maybe this is a point that we could highlight. Just remember, when we draw a graph, we're simply trying to give a reasonable picture of what the graph would be. Okay, we can't draw 1,000 points. We simply get an idea, understanding aspects of the function as to what a reasonable graph would look like. Now, of course, if you have a device that can plot 500 points, then of course the graph's going to have a really nice picture, but we don't want to be reliant upon something that plots that many points. We want to know, with just maybe checking out a few points and other characteristics of the function, that we can come up with a reasonable graph that doesn't require that much plotting of points. We want to keep the discussion mathematical, and then rise to the graph and know that we have a reasonable picture. Now, let's look here. We have x equal -2. Just compute f of -2, just as practice here. So we're doing the same thing again. And then we say, oh, excuse me, notice, not defined. Again, let's just go ahead and write down the domain. And I kind of set you up for this, and I shouldn't have done that. But let's just look at this. All x in the real numbers, you could do element of r if you wanted to, but we're making that assumption tacitly. So all x that are real, such that x minus 2 does not equal 0. We can't divide by 0. So of course, if we had a quadratic there, we could just factor the quadratic. So I'll give you an example of that. So notice when we see here, this just says x not equal to 2. So I'll do another one. I think the last one I did, I kind of left this part out, but it was clear. So x not equal to 2, just as an additional. And then of course we can do our interval notation, -infinity to 2, union 2 to infinity. So of course, if 2 is not in the domain, because division by 0 is undefined, then this is not defined either. So this point, this observation here, this evaluation makes no sense. Now, of course, when you think about it, just like the problem that we were thinking about before, I think I had a 2 in it. Let me check the last problem. Yeah, it's the same thing. We have a horizontal asymptote of y equal 2 here. So we get the same kind of problem. Now let's notice this. C, we have f of x equal 3. Well, let's write down the functional equation. So this says 2x divided by x minus 2 equals 3. So let's cross multiply. So we have 2x equals, well, 3 times x is 3x minus a 6. And now we can absorb the 2x into the 3x to give us an x, and then transpose the 6. So x equals 6. So what we're seeing here is that there is a unique input to give us the 3. There's only one. So basically now when we look at this, f of 6 equals 3. And then you can just look up here and see that. I mean, we notice that this is the same problem we've already done, but I didn't want you to think of it like that. We did the backwards problem, but it's good that it worked. So then we say if and only if, in this particular case, let's see what we have here. Oh, and what's interesting about this is just the flip. It's not exactly the same. Notice here, and this is interesting how the problem's set up. The instead of the x here, we see that the new value of 3 here, or y, is 3, and that's different here. So it is actually a different problem. So now what do we get? We say 6, 3 is an element of f, which is actually the flip of the coordinates that we have in A. So that's kind of a play on the parts here by the author. If you look at this again, 3 is mapped into 6, and now we see in this particular case that 6 is mapped into 3. So that's really interesting when you think about that. Now another thing that you might want to also consider is if we have this vertical asymptote, why does it appear, if you look here, the value here is 3, and then when it increases to 6, it looks like the values of y are getting smaller. And that's not a surprise. If you think about this, let me give you another sheet here. As I said before, let me just write a few things before I say a little bit more. We're going to have a horizontal asymptote of y equals 2, just because of the fact that the 2x over x will survive when x is large. The minus 2 here will have basically no impact. And we're going to have a vertical asymptote of x equals 2. So 2 and 2, but one's a horizontal line, one's a vertical line. So now I can get this on the same page. We can think intuitively. So we can draw a vertical line, and since it's not going to be part of the graph, we usually just dot it. So this is a vertical line, x equals 2, and then we have a horizontal line, y equals 2. So just doing a little basic arithmetic here. So we have y equals 2. Now notice, again, we have x-intercept if and only if f of x is 0. So that just means 2x is 0. The numerator is 0. So x equals 0. So we have an x-intercept of 0. Very simple. So we can go ahead and plot that. And now notice the y-intercept is the same. Y-intercept is just f of 0. 0 is in the domain, but f of 0 is 0, so we don't get anything new there. But notice, and this is what's kind of important about this, if we think of the BVs, we have 2 and 0, just like we had before. So we have 0 and we have 2. And now what we notice is that if we think of this as trying to figure out sign, these are all first degree in x minus 2. The zeros have multiplicity 1. So if we were, again, to put in the value of 100 for x, that would be a positive number. So we get just like what we had before with the circle. We get something like this. So we get above the axis below the axis, and above the axis. So notice here, from negative infinity to 0, we're above the x-axis, then we cross. So this sign test gives us a way to give us a reasonable graph without calculus until we get to it and know that what we're drawing is actually good. Something like this. So what's going to happen is that the graph will approach the horizontal line and also the vertical line. But again, here the graph has a positive value. Here it has a negative value. But up here, we have no more intercepts. So the graph has to look something like this and decrease into y equal 2. And that's exactly why the values here are decreasing. So when we input 3, we get 6. But when we input 6, we get 3. So the values here are decreasing. Now, of course, this is a reasonable graph, but ladies and gentlemen, we are using a lot of intuition. We're thinking, okay, well, it appears that the graph is decreasing here and also decreasing here. It never increases. And then that's going to be some definitions that we're going to have in the next section. So we'll talk about that. But what I want to impress upon you is that when you start computing points, you're going to ask yourself, why does it appear that the values are getting smaller here? I mean, you know, what am I doing here? You know, what's causing this? And then when we think about this, that will be something that we'll answer in the calculus. But at least intuitively, if we plot several points, we'll see that as we move to larger and larger values of x, the y values get smaller and smaller, but they never fall below the value 2. They get very close to 2. Likewise, over here, as x gets negatively very, very small, the values of the function get extremely close to 2, but not from above, from below. So here, approach to 2 is from above. On this side, approach to 2 is from below. And then, of course, the x and the y-intercepts, they coincide, so we only get 1 point out of that. So what is important about the x and y-intercepts is that we often think of these as driveways. For instance, as you look at this part of the graph, there are no x-intercepts. So you couldn't have the graph crossing the x-axis indiscriminately. So it's really nice with the Cartesian coordinate plane to use the fact that if we have intercepts, we have a way to cross, we have a way to change sign. But notice when we look at the sign convention here, it's very restrictive. The only places or the only interval for which the function has negative values is between 0 and 2. So we have 0 and we have 2 here, and that's the only place when the actual values of the function are less than 0. Otherwise, they're greater than 0. So our BV technique, looking at sign like we're solving an inequality, is extremely important, gives us plenty of information. Intercepts give us plenty of information. Checking values of functions, just seeing what's going on between different values of x. Are the outputs getting smaller? Are they getting larger? Is the function, you know, do we think of increase? Do we think of decrease? Or do we think of constant? Okay. So what I wanted to do with this lecture is just kind of give you the algebra of the functions. Now, in the next section, I'm going to talk more about some of the properties, and I'm going to also add some ideas about algebra functions that I think will be interesting to you. For instance, what do you do when you add functions? Is there a formal way to do that, or multiply and divide? Do we have a way to do that should remind us of the arithmetic that we've already been doing? And of course, the answer is yes. So I'll provide that with you for you, and also give you some more properties of functions that will make you feel a little bit better about the constructs that we will see as we continue through the course. Okay? So I'll see you next time for the next lecture. Thank you.